A very weird little behavior that humans engage in, and one that kind of over time has really grown to be almost mythical. When I talk to people about innovation, they sometimes picture like an inventor or some guy in a workshop, and maybe he's mixing some chemicals together, or maybe he's building something. But there's this general sense that for innovation to occur, there has to be some sort of aha moment. And depending on how you envision the scenario and what time period, either a candle or a light bulb lights up and they figure out a new way to do something that we already know has value, or they discover a new thing that has value that they're bringing to society, right? But what I want to try to do over the next kind of half an hour is present a case that there really isn't spark or necessarily kind of human aspect to innovation, but instead that we can approach innovation in a purely algorithmic sense. And by doing so, we can help automate a lot of the legwork. So right now, if you're an entrepreneur, or if you're an inventor, if you're a musician, if you're trying to sell yourself, you're trying to sell goods or services, you'll find yourself having to run your own business. That means networking, that means talking to people, setting meetings, getting to know who can be a supplier for you so that you can build your product or supply your service, and then who is your clientele. You got to get that message out, right? And a lot of that is a lot of hard work, a lot of stuff that's in person, and you end up being limited by the people you know, your physical geography, and it's weird that, especially now that the startup craze has really gone into full swing, and we have like, you know, Silicon Valley, and even in Seattle, and even in Toronto, like everything's kind of like geared up and going, and everyone's doing new innovative things. Somehow we're still using this archaic way of actually setting ourselves up to innovate. So for the first part of the presentation, I'm going to go ahead and just try to break down, like I said, innovation into algorithmic steps. And then we're going to see how all this kind of comes together on a platform, and then maybe discuss in the later half of the presentation. I'd really kind of want to open up the floor. I have some kind of guiding questions, and maybe we can have a little conversation about the implications of automated innovation, in a sense. So fundamentally, innovation begins with the observation of the world around us. We notice that something is amiss, or we wish that something weren't the way it was. The point is that we are able to recognize our current situation, and we know that we want to change it, that we're not happy with how things are. So using these observations, we can build a conceptual model of our current situation. So let's just kind of work with a simple example. This could be like a brick and mortar store, retail outlet. I don't know what they sell, but basically their customers are locals who come into their physical store, and they have some systems, like an inventory system, as you can see, some vendors that supply them, and of course employees. And this is kind of their current situation. One thing I'd like to note right at this point is you'll notice that this is a graph. And the concept of the graphs are going to come into play a lot here. And the reason being is I've never ever come across a data structure that's more flexible than a graph. I'm hard pressed, and I don't think I could give you an example of something you can't represent from reality as a graph. But anyway, so let's say that this is our current situation. We're the owner of this place of business, and we want to make some changes. Because it is 2017, we would love it if internet users could also be our customers. Now, of course, while they are still customers, they have a sort of a different user experience than the people physically coming into the store. Internet users wouldn't be coming into a retail store, they would be going to an online store. And that online store would have to interact with the existing inventory system. And of course, the staff that currently field the store would also have to be able to ship orders and handle, client requests that come in through that online store. So this is the sort of target state, right? And in a way, this is an innovation here because you're trying to build something new, at least for you. And more often than not, it's unlikely that there's a completely plug-in and play solution for what you're envisioning as a business owner, right? We know all obviously of many kind of stuff like ZenCart or WooCommerce. You can kind of download it, install it, and set it up. But let's say you're looking for something custom built, right? So let's take a look at what an online store really is. And what I want to highlight here is that each individual node that we had in the background that we wanted to add, so specifically the online store here, it is actually kind of abstracting away a lot of details about its own implementation, right? So these are things that the business owner would specify. Well, I want to have an administration console so I can look at orders, so I can look at transaction logs, what have you. He wants to have a sort of landing page where people come to that's separate from the inventory system, a catalog, obviously payment, and then naturally you'll have to host this somewhere. So we can see that there are multiple moving parts on something like this. And again, these details are hidden behind that kind of higher level target state that we were talking about a second ago. And what I really want to stress is that this keeps going. So if we move on, we see that the landing page itself has many subcomponents that make it up. So it'll need a domain that'll point to it. It might have some JavaScript files for interactive stuff. You'll have your banner image for the store, a small about blurb, a heading, various styles, and so on and so forth. And what I want to do now is kind of bring this information together into that initial state that we were talking about. So here I've brought in, what are we looking at the landing page, I brought it into this bigger graph. And what I'm going to do is I'm going to expand every one of the nodes to include more details. Now, keeping in mind, of course, that all of these themselves can likely be split up in even more details. And it really is, it's really up to the business owner or the person defining the state and how much detail they want to go, right? So this is a problem that if you've done any kind of consulting work, you'll know that the owner or the client kind of knows what he wants, and it's not what you just built. There's some little thing that he envisioned differently that when he said, make me a website, was there that was not communicated properly. So even though you're right, these definitions become exhaustive to actually put down, they have to happen even without an algorithmic approach. Even when you're just talking and doing this manual work, if you're hired to build something for someone, ironing out all these details is still a part of the process. And as we'll notice here, it is a part of the algorithmic process as well, to define all the entities that and the relationships between them that describe the desired state. And so if we take all that, kind of make it tinier and plop it in there, this is kind of our target state. This is where we would like to be in over X amount of time, however long. And let's formalize a little of this. So we have our initial context, and I'll be referring to that as such from now on. And then we have a final context, which is our desired target state. And like I said, I believe that all innovation really begins with somebody noticing a situation like this and really detailing down what it is that they'd like to accomplish that they can't currently. So now let's talk about steps, actions, and service providers. So these are other components of an algorithmic approach to innovation. And they're important because we interact with the world through our actions. In fact, actions are the way that we can transform these contexts. And any single action we can think of as a step. So we do a series of steps, and that'll take us from point A to point B. This can work obviously geographically, but it also works on a kind of a logical level when you think of a project. Okay, I need to build a website, there's going to be this series of steps. Now, when humans do this, you're leveraging the fact that you have, 20, 25, 30, 40 years of experience in having done this in the past. So the steps are pretty clear in your mind, right? You've probably done this before, and because of that, it seems intuitive, even when the client is asking for something a little different than perhaps what you had originally planned. You kind of have a gut feeling of how to approach a slightly different problem than what you've already done. And because of this, I think that kind of gives us a little, I don't know what the right word would be, but a sort of a sense that there's some intrinsic human spark about problem solving. But I don't really think that's the case necessarily. So let's look at an action just conceptually. An action fundamentally has to take some sort of input, some sort of current thing, and then it produces some sort of output, right? So an action could be me moving this pen, right? Where I take the pen as input, and then the output is that I've changed the physical location of it. But virtually any action can be thought of as, what do you need to perform this action, and what will you have once you have performed it? But this is very kind of high level and weird, so let's get a little bit more, let's look at a specific instance. So let's say that I'm a web developer, and I've written up a script that can actually generate landing pages given on a number of inputs, right? So I want, for my script, I want the heading, the about blurb, any banner image. I can let you choose a primary and a secondary color that I use to generate styles. I need a target folder on a remote machine. That's how I make sure that when the domain points, it points in the right location. And I'm going to charge you 5 cents for using my script because I put time and effort in debugging it, and that's how much I decide that that's worth to me. And that will produce a landing page. But more specifically, it'll produce also a landing page that has the domain pointed at it because of the target folder, the appropriate style sheets, the appropriate scripts, and the appropriate HTML files. And I'm filling those in values in those components from the inputs, right? So I know that this got very messy very quickly, but all that the dotted lines show is where I'm taking, for example, the about blurb, and I'm putting it into the index HTML. Or I'm taking the primary, secondary colors, and I'm sticking them into my style sheet, right? So some customization, but ultimately this is an action that produces this thing here on the right. But of course, as human beings, but also on a market, there are multiple service providers. There are a lot of actions, and these can be anything. So I have some examples here. There's my little landing page script. You could do some hosting on Azure. You could do payment processing with PayPal. Notice conveniently that I've brought kind of together exactly what we need for this example. But what I also wanted to show here is that a single service provider can provide multiple actions, right? So a single company might provide multiple different kinds of products or services. And in an algorithmic approach, I would imagine that we have a platform where we keep an index of these actions and who provides them, how much they cost, etc., etc. So for any action to be used in this kind of algorithmic fashion, it has to define its inputs and outputs in the way that I described here. Because when it does, we can do the following. So the big question, the $1 million question, if you will, is, okay, we have actions. We understand our contexts. So what series of actions take me from my initial context to my final context? How do I find that ideal path? And more than that, how do I find the optimal path, right? So before we get too far into that, let's formalize this idea of a problem. As we know, we've already discussed initial and final context, but in order to properly put a problem onto an automatic or an automated innovation platform, you'd have to describe 2 more things at the very least. One is the budget. How much money are you willing to spend to find that path that'll take you to your desired state? And then you'll also need a sort of acceptance criteria. So for your target state, it's great to describe it, but there's often a lot of non-functional requirements, such as maybe latency response on a server, or the fact that you want to be able to handle 10,000 concurrent users, or whatever, that could be written as actual test scripts. We already do this with integration testing, unit testing, whatever. So having those available, the more tests you have, it's as if you gave more details. So the higher the chance that what is being built is exactly what you want to have built. But ultimately what we use these tests for is we run them on the final context and we see if it passes all the conditions that our client, or in this case our business owner, says, okay, I'm happy, this is the online store that I wanted. Now, with all this, we are ready to start kind of building our solution graph. So we're going to start with our initial context, and what we look for is any kind of action which we have the inputs for to try. Now this is a very kind of brute force approach, but in many ways think of it akin to when you're debugging and maybe you're not quite sure what to do next. You've not encountered this problem before, so you take your best guess. You look at what you have and you try something that might do something. You might be wasting your time. In fact, that's why I find most of my debug sessions go like 9 hours of aimlessly flailing my arms and then like 10 minutes of just fixing a semicolon somewhere. So trying anything is a reasonable start, if maybe it'll eventually lead to kind of computational problems, a combinatorial explosion, but we can start here for now. So let's say that the first thing we want to do for an online store is we're going to want to secure hosting. And we'll assume that within the details of our initial context, we're given all the details that we need, you know, credit card information, the business owner's address, whatever. So we're going to pipe all that into the inputs for our first action, and our action is going to resolve, and it's going to create this kind of interesting intermediate state, which is the state that you were in previously, plus a small delta that the action itself applied to the state. So in this case, it would be going from where we were without a website, or I'm sorry, without any kind of hosting or anything, to a place where we do have hosting for a site prepared for us, in this case with Azure. And once we have calculated that delta and attached to the graph, we've now produced our first kind of next context, our I plus 1, if you will. Now, since we are looking for the most optimal solution to our problem, we are going to want to do this again with every other kind of action that could be applicable here that could resolve this hosting issue. And so we see how this works out. And if you think about it, what's going to start happening pretty quickly is this is going to blow up. Because the more actions we have available, obviously the bigger the graph gets, and very quickly it won't fit on a PowerPoint slide anymore. So you will notice, however, also that we are keeping track of the way that contexts work out. So here, I know that this isn't context 23 so much as it is taking context 2 from the first section and then moving with a third option afterwards. So we're keeping a sort of history of which way we decided to go through the solution tree in the, you can think of it as a property of a context, we keep that with it. And of course, these do blow up and kind of try to make a more complex one, you know, pretty ugly. But what will eventually happen is after some finite number of steps, you will reach a solution, if there is one, right? Certainly there are things that would create such a massive combinatorial explosion that you'd be computing for 30 years. And the equivalent in kind of human innovation is really, really big projects. So Elon Musk's plan to put people on Mars is going to take humanity 20 some years. because he needs to solve all sorts of these kind of, if you want to think of the solution graphs that he's trying to explore to solve, radiation in space. How do we shield people? How do we get food? How do we get them to be self-sufficient, right? So he has all these sub-problems to solve beforehand. So yes, there are situations where this algorithm would also trip up because it has so many things to consider. But more often than not, I feel like that has to do with the nature of the problem that you're trying to solve. You couldn't just put something like, find me the cure to cancer in this kind of system, because it too will, get stuck trying to find all, resolve all the subproblems required for that. And of course, since we don't know how many steps it will take to find the right solution, the whole unknown situation, there's no guarantee that there is a solution for your thing in a reasonable amount of time. But we're talking about a much more reasonable situation where we're trying to automatically build a website with a storm card. So here it's reasonable to assume that we have enough services built by other people that there is probably a finite and relatively short combination of them that will provide us with what we're looking for. And once we have identified those, and we do those with those acceptance criteria as I mentioned earlier, so after each step, we run our acceptance criteria on the context, and if we have passed, then we've reached a solution. You'll notice that the solution is really reached on the very final end here, and then we backtrack through our kind of decisioning all the way to find how we got there. So let's clean this graph up a bit because it's a little excessive. And you'll get your two solutions here in this case, right? So my father and I have been working on prototypes of this algorithm for a good couple of years now. And what we're kind of excited about recently is we were able to run some test problems on it and do some visualizations, which will kind of demonstrate what I've been talking about. So what you're going to see is a very, very short video, hopefully not too loud. We might not even have sound, I'm not sure. Yeah, no sound. But that's not particularly important. But what you're about to see is you're going to see a solution graph being explored. And then once the target context is reached, it's going to be pruned, just as we have here. Just a couple more things to note. So these little actors represent service providers, and they apply their actions onto contexts, which you'll see are going to come off as little nodes. And of course, what we have on either side here is entity definitions of initial context that we've gone through before, as well as these action definitions that I was talking about with inputs and outputs, right? So service provider is going to get the proper inputs and outputs from there, map it to the solution graph we're trying to solve for, and then see if it has reached the target state. So hopefully I'll be able to show this off a little. So there we go. So we're going to start exploring the solution graph here with various service providers heading over to grab the right nodes. And as they do so, eventually they do reach final solution here, and they trim away the other part of the tree that's no longer necessary. Now, we can configure this to do things everyone. It's an older video, but I digress. But we can configure things to what, oh yeah, please.
In that video, what's the dimensional space of the representation? Is that plane space or what?
I'm sorry?
What's the actual?
The actual it's just a little bit of a physics simulation on top of that. There's no, the vector space is not significant. Yeah, but what I just want to kind of show off again a little bit here is once we found our solution, we trim the excess part of the solution graph away, and we keep our found solution there. And with that, we're going to progress. So now that we have found a solution to our problem in this algorithmic fashion, I want to talk about something, a direct implication of it. Something, yes?
Actually, you keep mentioning an algorithm, but what algorithm are you using to search the solution space?
What algorithm I'm using to search?
Yeah.
So on the current face of things, I'm using a brute force search, right? Now, that is simply because right now I'm trying to do a proof of concept and show that this can measurably work. Obviously, the combinatorial explosion of that solution graph is definitely of concern. And there we can kind of leverage stuff like, particle swarm optimization, all the various kind of advanced in machine learning to maybe at least guide our search, if possible, to improve that performance. But really, optimize last. First, get it to work maybe on the smaller problem, right? Any other questions? Cool. Okay, so let's look at these two distinct solutions. And first of all, let's just really kind of pull them apart, right? So there's two there because of this decision point, arguably here. There's two distinct ways to solve this problem. And, let's forget about B, unimportant really. If we look at A, this is kind of what's going on there, right? So through the exploration of the solution graph, we've determined that there is a number of actions that performed in a certain order will take us to that final context. Now, does anyone kind of notice something a little cool about this structure? Yeah. It's pretty out there, but I'll give you a little hint. How about now? So the solution to any problem is an action in and of itself, right? Once we've solved something once, that can now go into the pool of actions that we are aware of. But more than that, you as the business owner or whoever funded this problem are now a service provider for a new innovative service, right? And you can put this back onto the platform and choose to publish it, and then people can engage your service at any point in time, 24/7. You don't have to be there, right? And you can charge them some amount. So considering cost here, a reasonable floor. Of course, you could keep this on at a loss if you're feeling very generous. But usually what I imagine a reasonable cost to a new service like this would be is at the very least the sum total of all the costs of the steps that make it up, right? That way you're at least not going negative when somebody uses your, your new process, right? And then more often than not, I bet, throw in a little something there for your trouble. But again, the big thing here is with this service on there, not only do you get your particular solution of an online store, but you also can build online stores for others. And that can be a source of passive income, which is kind of nifty. So the usefulness of such a platform definitely depends on the kinds of actions that it's aware of. And the more actions, the more versatile the projects. And what's really nifty, of course, is since the solutions to project themselves are actions, there's potential here for a very rapid increase of usability for the platform as a whole. So one thing that kind of gives me hope in the fight against the combinatorial explosion is that we're memorizing past solutions. We're using them to not recompute the entirety of the solution graph from scratch. And if you think towards various human innovations in the past, this has very much been the case, right? So if you were to write, a new program now, you're going to write it on an operating system with a high-level language that took, 50+ years of development. There's, virtual memory, virtual CPU time. Like, there's so much that you're building on top of, and it's almost like people who've crunched the numbers on solution trees underneath you so that you can use those results without you having to go in and, say, okay, how do we build a transistor, right? So let's yeah, please.
Question. When you said that you do brute force, I assume though that you're stopping once you find one feasible solution, or are you actually searching every possible?
So the way we have it done in prototypes now is we have it keep searching until some X number of solutions is reached. More often than not, that is set to 1. But if you want to look at multiple solutions and compare them amongst themselves to see if there's one that's more optimal than the other, you're free to let it crunch.
So you don't have any sort of measure that you're optimizing, and then some, so you know the optimality gap when they're
So the optimality, part of those tests and those acceptance criteria can define a sort of fitness in a more traditional sense. So for example, let's say that as this business owner, you're looking to minimize cost. So you'll always be preferring the cheapest action at the time that is applicable, right? But a business owner can also specify that maybe they're more after performance or scalability or whatever else, right? And then by setting these parameters, we can kind of set up a greedy algorithm that appropriately reflects the wishes of the client. So for this part, I really kind of want to, yeah.
Just have one, like from the first slide, it said you were from like some sort of algorithmic problem-solving group. I was just curious what the group was.
Oh, you're in it, if you're on the Meetup
Oh,
page.
we are.
Yeah, this is, so I started a Meetup here. It's a sister Meetup to one that my father and I started in Toronto last November. In Toronto, we have about 700 members registered. And then here, I just kind of came back for school here, so I'm just starting up. We're about 40-ish people on Meetup, and very, very great turnout. Let me tell you, like 700 people in Toronto, but we get maybe like 20 people out of them. So as regulars anyway. So really, really cool ratio of people that showed up. Bravo, guys! Props to you. Yeah. The Meetup in Toronto is called TCP1P, which ambiguously seems in no way related to this one. We don't have that branding thing down very, very great yet, but we also have one starting up with about 100 members in New York, and we hope by next year one in Montreal. And again, our goal is really to kind of plop this idea down on people. It's like, what if innovation didn't have to be this stroke of luck? What if we could develop a platform where we could systemically and consistently foster the processes that fuel entrepreneurship and innovation in society? And really, it's very much a discussion that we want to get going, because what we're proposing here isn't an app, and it's not like a social media site that you log on and put some problems and put your search on. What we're proposing would have to be a societal effort to kind of change the way that we look at problem solving, and to decide that, hey, you need that critical mass of actions on the platform before this becomes truly useful. So it's really about turning the gears and saying, with automation happening, and automation is a very hot topic right now, with a lot of people maybe losing their livelihoods to it. And what we're proposing is, like, can we build things in such a way that your average person can benefit from the advances in automation? Can we build things in such a way that you can passively gain money from the work that you've put in? How many coders and script writers and whatever spend time on hobby projects on GitHub, and you put work in there, and maybe that's useful to someone. What if that meant like you made $20 a month off whoever is benefiting off your little